The production of high quality food is very important to all of us and the consumption of that high quality food. And to go along with that, to protect the consumer, we need traceability systems. Now, there are some fantastic traceability systems around now that can pass information along a food chain, but recent food safety incidents have shown that not all systems are completely infallible. In fact, as a result of the horse meat incident over the last few years, the Elliott report from the UK came to the conclusion that there's been an over-reliance on traceability systems in themselves that will pass information. And if you realise that these systems are actually putting labels of some sort on the packaging, so they are tracing the packaging. We see that there is a place where the systems can break down. So one of the results from the Elliott report is the need for new ways of verifying the traceability, and that's where some novel analytical techniques come in. And the techniques I'd like to talk about are just some ways of making use of the inherent chemical properties of the food itself, so we can actually make traceability on the food and not just on the packaging. So there are two key reasons for doing this. First, of course, is the consumer protection and also the protection of the protection of the producers from the fraudsters. Because wherever you've got a high quality product, then there's a economic motivation for someone else to try to rip that off to make money. But there's another aspect that I would like to come back to later, and that's of the adding value itself by having these systems in place where you build the brand and so that the producer can get better market access and maybe better money. The two classes of techniques that I'm quite excited about would be the inorganic analysis, such as the stable isotopes and trace elements in the food, and there's another class where we look at the small molecules that are produced through the biochemical processes as the food is developed or produced, and that's the metabolomics. So if we start with the inorganic, the trace elements, I think that's fairly easy to understand how that works. You know, the plants get the trace elements out of the soil. The soils are made up of different types of soils all over the world, and so there are different trace element patterns. Those patterns are passed up into the food, and we can make measurements of the food and say, where would we expect this pattern to occur? The stable isotopes, it's a similar process, except the isotopes, we're not talking about radioisotopes here, these are stable isotopes. So if you think of carbon, 98.9% of carbon is carbon-12, about 1.1% carbon-13. Now that difference, it's because of the extra neutron in the nucleus. It's one of the most subtle chemical perturbations you can make to a system. And the carbon-12 and carbon-13 still undergo the same chemistry, but at slightly different rates. And so when you have processes such as in food with photosynthesis and then the other intercellular processes, you get this slight separation or change in the ratios of those isotopes that is driven by the environmental factors that we can make use of then. So food produced in one region, could be the same food, would have a slightly different isotope ratio to food in another region. Now this is very subtle, we're talking about differences in the 4th and 5th decimal place, so the measurements are pretty tricky. But the big advantage with the stable isotopes, and we're thinking of hydrogen, carbon, nitrogen, oxygen, sulfur, these are the elements of life, so they're the major components of the food. And we understand what these environmental drivers are. So for example, with the rainfall we get, there's patterns in the hydrogen isotope composition of rainfall all over the world. It's closely related to the annual temperature, the mean temperature. Now that pattern is then passed up through the food chain. And so we can make measurements on the food and say what sort of environment that would have come from. Of course, to do this as a traceability system, you have to know what the pattern would be for your food, for your production. So, and that's one of the problems with it, that it can be quite slow and expensive to collect the authentic samples, make the measurements, you define the specifications for your food. And then when there's a sample that's being a suspect sample, you make the same measurements on it and say, does it fit the specifications or not? If it doesn't fit the specifications, then you've got good reason to say this didn't come from that production. As I say, that could be slow and expensive, but if we make use of the stable isotopes, and this is where the novelty is in this technology, is we can make maps that are predictive. So we understand what drives the rainfall hydrogen isotope composition. We make use of the meteorological data that's been collected anyway and do predictive models. And so when we make measurements on our food, we can also use those models to predict what the composition of food would be. And so that means we don't have to have as many samples, makes it a lot cheaper, but it can also be very much faster, where we can just develop a model and say, what do we expect the composition to be? So either in the sense of what would a production unit look like, or if we get a suspect sample, say, where do we think this may have come from? So it's more predictive. So that's one of the big advances that have been made in this technology. The other analytical technology I think is very exciting is, I'd say, this metabolomics. Now, metabolomics are the small molecules, so less than 1,000 daltons. Now, these are the molecules that are the products or byproducts of the biochemical processes. And very subtle differences, such as the amount of sunshine that our plant is getting, can change the ratios or even the presence of some of these metabolites. Now, the advances in modern mass spectrometry mean that you can take a sample, say it could be honey or milk, and very quickly you can measure 10,000 molecules and quantify this huge number of molecules. Now, a lot of them aren't going to be much use to you, so the other part that's been advancing is the chemometrics, the way that you use statistics to filter those out and get down. So from the thousands of molecules that you had to start with, you come down to maybe a few hundred that are important, and then the really important ones, you might be 10 or 20 of them. And the high resolution mass spectrometers mean we can actually identify what those molecules are. So the two ways of doing this, if you've got the equipment to do the high resolution mass spectrometry, you do an untargeted analysis. You just measure everything. The huge advantage in that is if you're asking a question, for example, what floral type is this honey from, there will be a different set of molecules that would answer that question. But then maybe 6 months later, somebody asks, well, what country did this come from? You've got the data there already. You just go back and ask it, interrogate it again, and get out the different set of molecules that will answer that question. So once you've got the data in hand, it's just a matter of interrogating it appropriately. Once you have identified which of the molecules or the set of molecules that are useful, then you can go to what's called a targeted analysis, where you develop an assay that's just for those molecules. So for people who don't have the high resolution mass spectrometer, you may be able to do that on a standard HPLC or a GCMS, depending on what the samples are. And so it's making use of that same technology being transported to much lower tech instrumentation, which means that people aren't kept out of the field. So those are the exciting developments from the technology, from the analytical side. What I want to finish with is to emphasise that it's not just about fighting fraud and doing forensics. That's sort of what we get excited about. But if I take the example, when I was in Sri Lanka a few months ago and reading their newspaper, and it said there's 10 things about the economy, which is a very fast-growing economy at the moment. Number one, the growth is in tourism because of it's a fantastically beautiful country people want to go and see. The second one is that they're one of the highest producers of tea in the world. But the comment was that a lot of the profit isn't being made because they haven't developed their brand. Well, this technology, as you can see with the stable isotopes, the very things that drive the differences in the isotope ratios are the environmental factors. And so there's a direct link from that beautiful environment of Sri Lanka to the product that's coming from there. So this is an enabling technology that will help the branding, and furnishing that direct link between the product itself and its point of origin. And I guess that's one thing I should have emphasised at the start. What we're talking about here is not traceability in the traditional sense of passing information along a line, it's point of origin. So at any point along that line, you can take a sample and say, I can verify where it came from.